Video games are complex. Understatement of the century, right? Perhaps one of the most complex topics that is a universal bottleneck for beginners and experts alike is the concept of UVs. Now, I'm not talking about solar UVs, although game developers could stand to get a few more of those. I'm of course referring to UV mapping, a technique used within the digital space to project 2D images onto 3D models. That may not mean much to you as of right now, so before I get into explaining what UV maps are, let's first look at why they exist to help us form an understanding. You are likely aware that to hold and represent visual data within games, we use images. Depending on the type of game we are making, we often call these images something different, such as sprites for 2D games and textures for 3D games. At the end of the day, they are all simply image containers which hold pixel-colored data that we use to display artwork. Let's start with how we use and display these images within a completely 2D game. In a two-dimensional space, the only dimensions we are concerned with are the width and the height, our x and y dimensions or directions, respectively. Well, we know that digital images are two-dimensional, right? So since our image is already in the same dimensional space, there is very little we need to do in order to actually prepare it. Simply importing the images and setting them up as sprites within your chosen application is most often as much as it takes. So if we extrapolate that knowledge a little bit, for 3D games it would make sense to utilize images in the same dimensional space, right? Except what exactly is a 3D image? Here lies the real reason why UV mapping is used, and for many working in 3D is a necessary evil. 3D images do not exist, at least not yet, nor in the capacity that could be usable for games. And due to the nature of using 2D images to store our textured data, we are inadvertently limited by the dimensions of said resources. To circumvent this limitation, the process of UV mapping was developed to be what I will call a translator between our 2D textures and our 3D models. In most instances, creating a 3D model requires the development of polygonal faces to represent the surface of the asset we are making. In a modeling application, these polygons would exist in what is referred to as the geometric space, which I'll just call 3D space. In order to use textures on 3D models, we need to bring one dimension into the other. Because it is much easier to lose a dimension than add one, we opt for bringing our 3D model into a 2D environment. This environment is called the texture space, separate from the 3D space, and it is where we will be able to visualize both our 2D and 3D assets together. This environment allows us to bring in our textures and position the polygons of our models to capture the image data. Essentially, we're mapping coordinates between 2D pixels and 3D space, all done via our texture space translator. Now, I know you're probably thinking, wow, that's pretty complex. And you're right, it is complex. However, in your day-to-day life, you simply won't be interacting with UV mapping in this way. All major modeling applications already have their own implementations on how to tackle this obstacle in more elegant ways, by interfacing it as a UV editor. Fundamentally, it is all using this underlying theory of translating between texture space and 3D space. Like I've mentioned, in a two-dimensional plane, we refer to these dimensions as x and y. However, when we operate in 3D, we also use x and y with the addition of our third dimension, z. Now, normally this is fine, as the 2D x and y dimensions can be easily translated to 3D coordinates. But the x and y dimensions of the texture space are not directly corresponding to coordinates in 3D space, but rather represent coordinates on the polygonal faces of our models. So in order to avoid further confusion by using x and y naming conventions in our texture space, it was decided that we would instead refer to the horizontal and vertical dimensions as u and v, respectively. Thus where the term UV map actually comes from. Now, this has been why UV mapping exists, But how does it actually work? We'll be looking at this question in much more depth over the rest of the series, but essentially the process of UV mapping is what allows artists to unwrap their models and provide them textures. Again, that may not be an immediately satisfying answer, so let's unpack what unwrapping a model means. Let's first look at origami, the art of paper folding. It may not look like it, but origami and UV mapping are actually incredibly similar, albeit in the reverse order. For sake of argument, origami starts in a two-dimensional space as a flat piece of paper. The process that then proceeds to unfold, or rather fold, is the transformation from a 2D item to one that exists within the 3D space. Now, obviously the paper exists within the 3D space the entire time, however, the concept remains the same. With 3D models, we already have our paper folded into our design, but we need to find a way to take our paper and flatten it back out to a two-dimensional item. Modeling applications provide us the ability to insert what are called seams. You have probably heard this term before, likely relating to seeing a texture misaligned on a model where you can see this seam line. What seams allow us to do is non-destructively tell our application where to make cuts along the faces on our model to better unwrap it in its attempt to flatten a 3D model into a 2D space. Origami may be difficult to picture here, so we can also think of inserting seams as the seam lines of a shirt. In order to flatten out a model, we may need to entirely cut off various areas of our model from other parts, much like how the fabric for a shirt is in separate pieces before it is stitched together at the seam lines. Now, there is no right or wrong way to add seams, as we will learn in this series. However, there are certainly better methods and rules of thumb that artists follow to maximize their space, since games often have a very finite amount of space available for us to unwrap. As we unwrap more and more parts of a model, the more crowded our texture space will become. Here is where film and games begin to differ a little. Unwrapping for films is more oriented towards making texturing far easier for the artist, as there really is no limit to the amount of textures they can use since everything is not rendered in real time. The optimization here is that an artist that can texture quicker is an artist that can work faster. Because of this, UV unwraps of models can look rather spacious and somewhat easy to identify even at a sheer glance. For games, this is simply not the case, as they need to be rendered at 30 to 60 frames per second in real time, with potentially multiple players and possibly thousands of other textured assets. Therefore, there are incredibly harsher limitations, as UV maps are intended to be optimized for performance instead. This will be where the focus of this series lies, in understanding how we can unwrap UV maps with a game-oriented mindset. In the next video, we will have our first hands-on look at unwrapping a simple 3D object to see what it looks like in a real-time modeling application.